Traditional geopolitical analysis treats crises as isolated historical events driven by the choices of individual actors. Systems dynamics offers a more rigorous alternative, modeling global conflicts as coupled, high-sensitivity networks. The Middle East escalation of early 2026 serves as a primary case study to test this networked framework. This crisis presents a distinct paradox: the coexistence of extreme military volatility with simultaneous high-level diplomatic negotiations. The result is a total breakdown in forecasting, with specialists, politicians, and the public producing a massive spread of contradictory predictions. The Brain Kinematics Model, or BKM, was designed to cut through this noise by treating the crisis as a physical system. Under BKM, crises are understood as the structured release of accumulated strain through pre-existing historical streambeds. This foundational BKM equation maps the crisis state to 5 specific structural variables: power, ideology, economy, control, and memory, all multiplied by the ignition trigger. To understand modern escalation, we must set aside the historian's narrative and apply the mathematics of a structural engineer. At the node level, we calculate the internal strain of a single nation using this weighted sum of 5 streambeds. We begin with the inequality of power structures and the intensity of ideology, which serves as a lens for belief absolutism. To this, we add economic deprivation gradients and the relative rigidity of internal control systems. Finally, we factor in unresolved historical memory, which acts as the binding force of the entire equation. Memory serves as a structural attractor, pulling current events back into the gravity of old, familiar conflict patterns. We see this attractor at work in 2026, where the strategic assumptions of the war were pre-shaped by the unresolved legacies of the 1982 and 2006 Lebanon conflicts. These 5 variables establish a total strain load long before the system encounters a trigger event. When these variables are loaded to maximum capacity, the internal strain equation leaves the state primed for systemic failure. Moving from a single node to the global mesh, we apply this finite element equation to track the interaction between the US, Israel, Lebanon, and Iran. The variable T sub ij represents the transmission coefficient, the physical and political strength of the edges connecting different states. These edges range from high-amplitude military proxy wars to the medium-speed, widespread effects of global energy markets. The Strait of Hormuz acts as a thick economic transmission edge. When land-based strain spikes, the resulting choke point anxiety impacts global energy prices within hours. Sudden shocks, like military strikes, are mapped as external inputs, labeled I sub I, that inject fresh strain into specific nodes. Conversely, dissipation capacity, represented by D sub I, shows how diplomacy or economic resilience removes strain from the system. The reason a local trigger generates a global shock is due entirely to the specific topology and thickness of these transmission edges. When we apply constant stress to this coupled network, we can measure its stability over time. This phase diagram tracks the evolution of the crisis, plotting accumulated strain against stability capacity. A horizontal dashed line marks the critical boundary, separating the stable zone from the region of war and collapse. A system's proximity to this boundary is a function of the ratio between its current strain load and its stability capacity. During the February to April 2026 Middle East escalation, the system's trajectory moved steadily upward from the stable zone towards this boundary. Rapid-fire inputs, including missile exchanges and maritime disruptions, kept reloading the system's strain faster than dissipation mechanisms could work. This high input refresh rate causes the system to vibrate at a frequency it cannot sustain, leading to structural buckling. Escalation becomes inevitable once the input rate mathematically overwhelms the dissipation rate, forcing the system across the boundary. This data point, lingering near the boundary, is a bifurcation node, the point where realized history ends. At this level of tension, the future trajectory can no longer be modeled as a single deterministic path. Instead, the system branches into a probabilistic fan of potential paths, known as strain arcs. Forecast dispersion is the mathematical measure of the spread of these arcs. A high dispersion index explains the wide variance in predictions currently coming from intelligence and media analysis. For the 2026 crisis, the BKM identifies 4 arcs: de-escalation, controlled oscillation, escalation, and phase transition. Controlled oscillation, a cycle of localized strikes and temporary stabilization, remains the most mathematically probable outcome. By using BKM, analysts can shift away from trying to pick a single winner and instead map the dispersion and boundary of possible futures. This framework allows us to revisit the question of whether geopolitical crises are man-made or systemic. BKM initiation data shows that for interstate wars and proxy conflicts, 80 to 95% of triggers are traceable to deliberate human decisions. However, while the spark is human and contingent, the resulting outbreak pathway is systemically determined by the network topology. Once an initiation occurs, the resulting energy waves are strictly constrained by the pre-existing streambeds of the system. This structural constraint is why history produces recurring strain arc families rather than random events. We saw this pattern in the 1973 energy shock, where conflict hit an energy node and triggered global downstream inflation. In 2026, though the technology and actors have shifted, the underlying mechanism of conflict-driven commodity shocks remains identical. The Brain Kinematics Model allows us to map these streambeds and bound the probability space of global risk. The world system functions as a topological spiral. While variables and technologies evolve over time, the underlying patterns of strain accumulation and release are permanent.